Before we move on to a new design pattern, I would like to talk about a subject that's relevant to inheritance. Remember this slide over here when we started reviewing inheritance, we said that code reuse is only one aspect for inheritance. In some way, it's kind of superficial. If you're only using inheritance for code reuse just to satisfy single choice principle, it may not be sufficient for the complete understanding. And we talk about, for example, the second aspect about substitutability, which is about polymorphism and dynamic binding. And we also talk about expectations and accordingly the rules for substitutions. And mainly about compile time type checks and also how we do typecast. And how you can result in a situation where you got runtime assertion errors. So these are the topics we review from the previous lecture. And in this small lecture, I would like to talk about subcontracting, which means in case you have inheritance, how are the contracts in the parent class going to be inherited to the child classes? And specifically, how do we check those contracts at the runtime? So that will be the main topic for this lecture. Let's see what the learning objectives are for this lecture here. Number one, we want to talk about preconditions. And we want to talk about the notion between require less versus require more. And similarly for the post condition as well, we want to talk about ensure less versus ensure more. And you can think about in the class invariance is actually included in the discussion for post condition. Remember from our previous lecture, we said that think about invariance as the post condition for every routine, right? You want to make sure upon the completion for every routine, the class invariance, the integrity constraints for the class would be maintained. And number three, we want to talk about the static analysis for inheritance and contracts. So statically, how can we know or justify that the contracts in both the parent class and child classes together are making sense or logically correct or logically sound? And number four, once we understand statically how we can analyze the contracts, but at the runtime, how are we going to check the contracts for the child objects? Because when dynamic binding is in place, the correct version of the routine that's defined in the child classes will be called. But now when we call that particular version of the routine, how are we going to check its precondition and postcondition? So that will be the subject for learning objective number 4. We'll see exactly how we can do it. Alright, so let's now review some background on what you learned in 1090 for predicate logic. Let's now consider two very simple examples, but you can definitely extrapolate to the more general cases for any predicates returning Boolean values. The principle will be, whenever you think about predicates, they simply just return Boolean values. And to think of it, you can think about it's basically a set of satisfying values. Okay, so this will be the guiding principle for interpreting. Every time you're given two predicates, you want to decide which one is stronger and which one is weaker. So to really do that, you basically just have to think about a subset relationship between the corresponding set of satisfying values. Okay, let's take two examples over here, this pair of example. Let's say for the first one, when you got x larger than 3, so this will correspond to one set of satisfying values. So if you think about this will be the corresponding set for that particular predicates. So because it's strictly larger than 3, so the smallest value we can start from will be 4, and then 5, and then 6, all the way to infinity. Conceptually, of course, in the context of computing, it may be only up to the maximum integer for the 32 bits storage. But for now, let's just be mathematical. So what about the second one? So the second predicate over here is x larger than 4. So you will have another set over here. And then we'll try to say what's the smallest allowable value for this set? Well, because it's strictly larger than 4, so the smallest one will be 5, and then 6, and then all the way to plus infinity. So these are the two sets. And now, in order to decide whether the green one is actually stronger or the pink one is actually stronger, we will have to think about whether one set is a subset of another. Okay, so now let's take a look. Well, apparently you can see from these two sets, you can see apparently this set here is strictly larger than the set over here. So to be more precise, you can think about this particular green one, the pink one over here is actually a subset of this particular green, the green set over here. Of course, you can definitely think about it's even a proper subset, but even though this is actually true, but whenever we talk about a set being a predicate being stronger than the other, we only have to consider a subset relationship. We don't have to go into the proper subset relationship. So this will not be necessary. Okay, I just put it there just for you to consider. Okay. So now we know that this particular relation actually holds. So now let's draw another diagram just to visualize it. So we are basically saying that this particular green set is actually strictly larger, okay, and then it will actually contain every possible value that's in the pink. And now we want to know if this is the case. So which is the value that's actually in the green but not in the red, right? So there will be a particular value over here that's actually outside the boundary for the pink. Well, based on what we have enumerated, so it should be simply just 4. Okay, so we know that in some way the green set over here is more accommodating. It's more accommodating. And of course, it's larger. And we say that it's weaker, this predicate over here. So whenever the corresponding satisfying value set is actually larger, we say that the predicate over here is weaker. On the other hand, if the corresponding set for the satisfying value for a predicate is actually smaller, in that case we'll say that it's stronger. So this one will be less accommodating. Okay, it's actually a smaller set, and then we say that it's actually stronger. So when we say weak and strong, it's typically a relative notion. So you have to compare two predicates that's given to you. If you can somehow have this particular subset relation, you would say that the smaller set is actually the stronger one, and you would say that the larger set is actually the weaker one. So the corresponding predicates. Okay, let's now get it right. Let me just annotate one more. So you can think about this particular one. That's actually the bigger set over here. So that's why you can see the strictly larger set. So you would say that x larger than 3 is stronger. On the other hand, if you try to look at the inner set over here, that's smaller or equal to. Okay, so you would say that typically it should be whenever you want to justify or to prove, you want to prove that it's actually smaller. Okay, and then this set over here. So this will be x larger than 4. So x larger than 4 is, hey, beg your pardon. Actually, I said it the opposite. So this larger set should be weaker. Okay, sorry about that. Is weaker. Weaker in the sense that the predicate is actually weaker so that it can allow more values than the stronger predicates. And this x larger than 4 is stronger. Okay, so what's the take-home message for this particular illustration over here? So whenever you're given two predicates over here, in that case, if you are asked to actually to determine which one is stronger and which one's weaker, you want to think about whether you can draw such subset relation over here. If you can, so that means the left-hand side must be the stronger one, and the right-hand side, being the larger one, should be the weaker one. So you have weaker versus stronger. So it's a relative notation. But you might be wondering, are there any predicates that's absolutely the strongest or absolutely the weakest? So let me pose this question to you, which we'll talk about later in the lecture. So think about what would be the weakest. What would be the weakest? And also what would be the strongest predicates? So the weakest means the set is so big. So any potential predicates, its satisfying value set will always be a subset of the weakest set. Okay, and symmetrically, the strongest predicate over here its satisfying value set is so small so that any predicates for any satisfying value set, the strongest predicate satisfying value set will be a subset of that. Okay, so that's kind of these two extreme cases. What will be the corresponding predicates for weakest versus strongest? Think about it, and we'll get to the answer for that a little bit later in the lecture. All right, so let's now go back to the slides. Having this notion in mind, we can now see how we can apply these concepts into the context of precondition and postcondition. Let's go back to the slides. Let's discuss the precondition first. So let's say we are given two preconditions, P1 and P2. So P1 and P2 are simply just predicates returning Boolean. So we say that P2 requires less than P1. So you can think about when we say require less, so that means we are being more accommodating about the input values. So P2 can actually allow more input values than what P1 can allow. So that's why P2 requires less than P1. If P2 is less strict and allowing more, that's exactly what I just said. So if you want to make it more formal, you can say that the set of satisfying values for P1 is actually a subset of the satisfying value for P2. So if you now apply what we said previously over here, if you look at that, you can think about the P1 over here is really the left-hand side over here. So P1 is a subset of P2 because P1 is actually more strict than P2. So we say that P2 is actually weaker, so it requires less. And P1 is actually stronger, so it require more. So just try to get used to such terminology, when you talk about predicates, especially in the context of precondition and later on postcondition. So let me go back here. So more precisely, we want to say P1 implies P2. So that's exactly the implication you want to always think about when you want to formulate the relation between the predicates. Let's see one example over here. Let's say we talk about withdraw command with simply just the amount. And we want to consider two possible preconditions. Either we say, let's say P1 over here, the amount is strictly larger than 0, versus if the amount is larger than or equal to 0. Think about this is some design choice you will have to make as a designer for the command. Which precondition should you use? There may not be right or wrong answer, but you have to know what's the consequence of choosing one but not the other. So let's now go back to iPad over here. And let's talk about the design choices we have to make. So if you look at these two alternatives for your precondition design, let's say P1 over here versus the P2 over here. So you can think about the P1 versus the P2. We want to think about which one is actually stronger, right? So that's the notion you want to always keep in mind in order to formulate the answer. So now if you go back here, so we want to know which one is really the left-hand side and which one is really the right-hand side. Right? We already said in the slides. Apparently, the P1 over here is actually stronger versus the P2 over here being weaker. So over here you can think about what we're doing is P1 over here versus the P2. And this is the implication relation you will have to justify, right? So now, again, how do we justify that? If you want to prove it, you can if you want to prove it to really show that P2 really encompasses all the values that's in P1, but also additionally P2 contains something more. So you can simply draw a diagram over here. Let's say this will be the set for P2 over here, and then let's have another set over here for the P1. So this will be P1. So what will be the value that's in P2 but not in P1? So in this case, it'll be quite easy to tell because P2 does allow 0. So this will be just a 0. That is an easy case. But sometimes maybe the precondition you have to, the alternative for the precondition you have to determine may contain simply a range of values, like a set. In that case, you have to be more careful. All right, so that's about the subset relation that we have. Let's now just illustrate a little bit more. So we know that P2 over here is actually the weaker one, given that we already justify the implication over here, right? The blue one. And also symmetrically, so this will be stronger. Let's now illustrate this very quickly. So whenever you're using a stronger predicates for your precondition, so that means this one here is requiring more. Whenever you're using a weaker predicates for your precondition over here, so that means it's requiring less. But how do we see that? Okay, so whenever you say requiring more, so that means less input values can be allowed. Let's see exactly what I meant. So let's be careful over here. So now we got, let's say this will be, let me just highlight it. Okay, so this will be version number 1. I'm going to use a pink, and this will be version number 2, and then I'm going to use a green. Okay, so these two versions. Let's say for version number 1, so we're going to say withdraw. I'll just say W, withdraw V1, and then I'm going to use all the 3 input value over here. Let's say if I try to make a call to say 100, so this will be 1 input value. And then if I say withdraw version 1, and then I'm calling by the second input value 0. And then for the third one, withdraw V1, and then minus 100, right? Okay, let's put the call over here, and then I will talk about together with the second version. What about the second version? The second version is simply just version number 2. I'm just going to call with the same set of input values, and then we can do the contrast and comparison. So now version number 2, we're also going to invoke on input value 100 and WV2, and also 0, and also W version number 2, and also minus 100, right? So now we want to know why the stronger predicates in this case, why does it require more? Why is that the case? So now let's think about what the consequence is. So now if you try to say call the version number 100, so 100 larger than 0 is going to be true. So you can simply say it's going to be, just say normal. Normal means you're actually going to execute the body of the implementation for the command and do whatever that's necessary. So what about 0 over here? Apparently for 0, if you say 0 larger than 0, it's going to be false. So this will be violation, specifically precondition violation. And what about minus 100? Well, that's quite obvious. Minus 100 larger than 0 will just be violation. Okay, hopefully you're following so far. And what about if you try to do the same similar reasoning for the second version over here, version number 2? So now if we do 100 larger than or equal to 0 is going to be normal. And then what about the second possible input value 0? So 0 larger than or equal to 0 is also going to be satisfied as a precondition. So this will also be normal. So this really highlights the difference already, right? Because you can see for 0 over here, that's the value that's allowed by P2, but not by P1, right? And then what about the third one, minus 100? Well, this one equally equal to the version number 1, minus 100 will not be allowed by this particular precondition. That's okay. So this will be violation. Right, so you can see the one that we should really pay attention to is, in one case, input 0 is actually going to result in a violation. In one case, input 0 is going to be just normal, which means it will be accepted as an input from the clients. So that's why we say over here, this particular P1 over here is a precondition. So the P1 over here, let me just write it down. So the P1 over here, we can say that it actually is stronger predicates that we are using. So that means we are requiring more from the clients. Meaning that, for example, you can see this 0 over here is actually not accepted from the clients. On the other hand, if we try to look at P2 over here, so if you look at the P2, we know that logically speaking, the P2 predicate over here is actually weaker, meaning that it will require less. Require less in the sense that you can see over here 0 that's actually not required. That's actually really 0 that's actually not acceptable by version number 1, but it will be acceptable by this version here, version number 2. So that means it's requiring less from the clients, right? Because normal will just be accepted. All right, so that's about how you can compare, different alternative for your precondition design, and then using let's say logical analysis, right? So the example I'm using here is really simple predicates, but you can definitely try to prove or justify about implication for any arbitrary 2 predicates that you're given. Okay, so that's about the precondition. Let me go back to the slides and finish off one more point. So what is the precondition that requires the least So basically, the weaker the predicate is, the less is going to require. The more, exactly, the less is going to require. So now, what would be the weakest predicate, basically? Well, hopefully you got the answer already when I asked you to think about in the previous exercise. It should be simply just true. So think about if you simply put a precondition true for your routine. So that means any client value that's passed will be accepted always. You can never ever have a precondition violation. So that's really requires the least. It might be possible for some routine, but I would say in general, if you simply got a precondition being true, you want to really justify why it should be the case. There might be some input value that might be accepted. However, it might actually cause some error in maybe later. For example, let's say if you're trying to design a precondition for division, in that case, if you want to say x divided by y, so if you simply say the precondition is simply true, in that case, it wouldn't be a good design, because what if the y, the divisor, will be 0? In that case, it shouldn't be accepted, right? So that's kind of the design choice you have to make. More precisely, let's now illustrate this precisely to make sure you really understand it properly. Let's say this is the divide routine that we are writing. So let's say divide, and then we got x and also y of type integer. And then that one there is also going to return, let's say, the quotients being the integer, right? You can also make it real if you want to get precision from the division. And apparently this is the dividend, and also this is divisor. Let's say the current design is simply that I don't have any precondition. I simply just do whatever implementation I need for the efficient division between the two numbers. Okay, whatever it is. I'm just omitting the details here. So now, if I don't put any require over here, it will be as if I set require over here, simply say true. So true, that means any combination of the input x and y is going to pass true always, right? So you can think about this is the weakest precondition you can ever get. Weakest precondition imposing no constraint on input values. Or it's also requiring the least, right? That's something we said in the slides. I'm not going to repeat it. So now in this case, so that means you would be allowing, for example, the consequence of this is you can even say divide. And then I can say divide. I want to divide maybe 3 by 0. Apparently, you can see this one is going to cause error. Okay, it's going to be a runtime error because of division by 0. We know that very well. Mathematically, simply undefined. Given that this is going to result in error, so now we want to know why we have such runtime error. Whenever you have runtime error, it's definitely the problem for the design of your routine. So now you should really say the error is actually because precondition weaker than necessary. In this case, because true is definitely weaker than necessary, so we should really impose a precondition that's actually stronger than true. So how can we fix this? So a possible a fix for that would be, so for example, a fix would be we can simply say require, and we want to impose a constraint to allow less value that can be passed for the divisor. So I can say require, let's say y should be not equal to 0. So apparently you can see now, you want to compare these two predicates. You got y is not equal to 0 versus true. Apparently this predicate over here is stronger than this predicate over here. So we are requiring actually more on this particular, by using this particular precondition, right? So in this case, apparently this will be the correct answer rather than this one. So what I'm trying to demonstrate to you is every time when you are trying to think about precondition and later on postcondition, always think about what are the alternatives. In which case, either go for the stronger one or the weaker one is completely up to what the consequence might be when you choose one, right? In this case, if we simply choose the weaker precondition over here, in that case, we're going to result in runtime error. So that's why a stronger one should be the way to go. Okay, so hopefully the precision is well communicated to you right here.